Yes, science and religion. Is there a conflict? Well, yes and no. Or it depends. Is one right and one wrong? Are both right? Are both wrong? Well, look at first science. Science does not have the answer for some of the most fundamental questions. It does not, for instance, know how everything came about, how the universe started. Religion, on the other hand, if everyone follows a particular religion and they think their religion is right and anybody else is wrong, then they can't all be right. Or maybe they can be all right. Or they can't be all wrong. If you look at the fundamental things of religion, then maybe they're all right. Because all of them believe in there exists something beyond the physical. Something that cannot be explained, perhaps, by science. Science deals with the physical. It breaks everything down to what components, what things are made of, and how those components react to each other. How the world works, the physical world works. Whereas religion transcends beyond the physical. It's the mind, or if you like, the spiritual. Now, if you go to the really fundamental religions, like that practiced by the Islamic State, and if they believe that the religion has to dictate is everything they do, everything they think, they say, they do, or and even what they wear. And if you don't, you're dealt with very severely. I believe it was Sullivan, a CBC, Canadian Broadcasting Company journalist, went over and interviewed a prisoner in Iraq from the Islamic State. And he said, well, if your religion is recognizes Abraham, then maybe if you don't want to follow our practices, you can leave. But if once you are in that religion, you have to follow all those practices. You don't get the option of leaving. And anyone that demonizes the religion is tracked down and eliminated. And they feel that their religion is the only right religion, and everybody else are infidels and should be eliminated. Now, in the more modern religions, no, we think more of an ecumenical movement, especially in the Christian religions, that yes, we have different practices, but no, we have the same fundamental belief or ideology, and we don't necessarily demonize the other religions. Maybe we used to, but because we all have the same fundamental beliefs, and the differences, the similarities outweigh the differences. We still will probably want to practice our own religion. So there's different ways that you can practice a religion, and maybe they all aren't wrong. Maybe they're all right. Now, first of all, let's look and see. Science sometimes argues that there's no such thing as the spiritual side. Everything can be explained by the science. Well, Persinger did an experiment. He took students, and unbeknownst to them what the experiment was all about, put helmets on them with magnets on the helmets. started off with a hockey helmet. This was at the Laurentian University in Sudbury, Canada. Then he put the magnets were to measure the brain waves. Then he put the students in an isolation booth, devoid of any ambient electromagnetic radiation or field, and devoid of all their senses of sight, sound, and touch. Then he looked at the brain waves, found that the left brain was shutting down and the right brain was getting more active. Then when he brought the students out, 4 out of 5, and asked them what they experienced, 4 out of 5 said they experienced out-of-body experiences where they felt that they were outside of their body. Some said they felt there's someone beside them or behind them. They saw tunnels of white light. Some said they thought they saw demonic creatures. Excuse me. Or some said they saw God. So as a result, it's been nicknamed a God helmet. So that sort of indicates that there are two separate domains, the physical and the non-physical, or the spiritual and mind. So if the scientists say that it can explain all that, I'll ask them about what that thought is composed of. And for instance, how many quarks, which is the smallest unit of material that we can come up with, how many quarks does it take to make up a thought? And with science, you're supposed to take it back to the lab and do an experiment to prove that the theory or the fact is correct. So you can ask them, well, how about you taking and creating a piece of my mind in a lab? Okay. So I think we could say that science cannot explain everything. Now, science is actually can never explain absolute truth, because science should be based on empirical evidence. When you come up with a fact or a true theory or a law, it should be based on evidence. And if you have a piece of evidence that doesn't comply, you have to scrap the so-called fact, modify it, or say it only applies under certain conditions. So you specify when it is correct. So really, you can never really state absolutely that it is the truth, because there may be another piece of evidence that comes up that you discover or that doesn't comply. Now, where are the things that the science cannot understand or explain? One of the basic ones is the beginning of the universe. Now, before 1929, everyone thought that the universe doesn't expand or doesn't contract. But Hubble, using the largest telescope on Earth at the time at Mount Wilson Observatory in Los Angeles, he saw that all the stars were going away from the Earth. What does that mean? It means that the universe itself is expanding. So if the universe is expanding, then it must have come from smaller and smaller and smaller areas. And if you go back, figuring out how fast it expands, you can go back and it turns out to be 13.8 billion years ago. It came from something, say, as small as an atom, where everything, the whole universe is in combined, started off there. And what does it mean? Time equals zero? Well, how can time not exist? And what was there before time equals zero? These are questions science cannot answer. When you deal in mathematics, when you divide by a smaller and smaller number, you get a larger and larger entity until when you divide by zero, all hell breaks loose. You get a singularity or infinity. And at time equals zero, we say that is a singularity. So is there something finite, something infinite then, that creates the finite, something that has a beginning? Again, science does not have an answer. But as I say, maybe it points to the fact that we have something beyond the physical. We often think of God as being infinite, for instance. Now, Planck, back in the early 20th century, said, you can't keep on dividing time down. You start off with 1 billion years, go to 1 million years, a year, a month, a week, a day, an hour, a minute, a second, a microsecond, and then you keep on going down, dividing, but you get to the smallest unit of time, 10 to the minus 43 seconds. That's 0.00043 times. You couldn't go no farther. Now, and they call it a Planck time. 1 Planck time is the amount of time taken to light to travel 1 Planck length. And a Planck length is 1.6 times 10 to the minus 35 meters. So space and length you cannot continuously divide down as well. So when you get down to the first Planck time, beyond that, science cannot explain it, because it's a small it's smaller than the time it's allowed to be. Now at that time, as I say, there's all the forces are together. They call it a super force. If you want to call it something omnipotent, you can, I guess. And then at the first Planck time, the force of gravity separates from the super force. Now there are all 4 forces. There's the force of gravity, there's a strong force, weak force, and electromagnetic force. And I'll explain these later, but for now. And we know, and then during that first second, more things happen perhaps than the rest of the 13.8 billion years. Now, 10 years ago, they would have told you it's 13.7 billion years. So here's his example then. Well, they must have found some new evidence, and so they've modified their so-called scientific fact from 10 years ago. And so don't necessarily follow hook, line, and sinker. When someone says it's a scientific fact, well, what they should say, it's so far, it has all the evidence supporting that particular fact. It's truth as we know it so far, or it's closer to the truth. But there may be some other in the future that we discover that says it's not quite true as we thought it was. In this case, you had to modify it. In other cases, you may just scrap it. And in other cases, you may say it just applies to certain phenomena, certain areas. And often there are colossal mistakes by reputable scientists. If you like, you can say science is based on making mistakes and correcting them. So you have a hypothesis, you then test it out by seeing if the evidence supports it, and then if you can, take it back to the lab and do an experiment, and to prove it's true, and then have it corroborated by someone else. so often, especially when you get into what you should eat, what's good for you, what isn't. There's so many scientific facts and theories, and perhaps they are too anxious to publish rather than have it corroborated before they publish. Now, as I say, science tends to break everything down. It uses reductionism into the smallest parts and see how they all work together. For instance, you are made up of atoms, molecules. Actually, you're made up of 65% of you is made up of water. And water is a molecule with 3 atoms, 2 hydrogen and 1 oxygen. Now, atoms are made up of a nucleus of protons and neutrons surrounded by negatively charged electrons. Now, normally there's the same number of protons as there are neutrons as there are electrons in an atom. The exception being being hydrogen, which only has 1 proton and 1 electron. Now, you are made up of mostly hydrogen atoms. You've got more hydrogen atoms in you than any other atoms. So you're more than 50% hydrogen. At least your atoms are. But the size of the nucleus of an atom is to the size of the atom as a speck of dust is to the size of a football field. So you are mostly space. You are 99.9999999% space. So if you think you can't be heard or seen, well, maybe that's the way it should be, because you're all space. Your atoms are made up of, are surrounded by electrons and made up of protons and neutrons. And your neutrons and protons are made up of quarks, up and down quarks. So you may have some days where you have your ups and downs. Well, actually, you're all physically up and down quarks. The up quark has a charge of 2/3, and the down has a charge of -1/3. So 2 up and 1 down, plus 2/3, plus 2/3, -1/3 is a proton, and 2 down and 1 up is a neutron. -1/3, -1/3, plus 2/3, 0. And science has a particle theory where they say the whole world, if you like, is made up of these particles and forces. There are 3 pairs of quarks. There's the up and down, which you are, and there's also the charm and the I forgot what it was now. Strange. Charm and strange. And there's a top and bottom. Those latter 2 don't stay around too long, so everything's pretty well up and down. Then with each of those pairs of quarks, there's a lepton with the electromagnetic charge. It's an electron. With the up and down, I think it's a yeah, as I say, for each one of the pairs of the quarks, there's a lepton photon associated with those pairs. The electromagnetic is the electron. A strong force, I think, is the tau, and the weak force is the muon. I may have those two interchanged. And then there's the four forces. Force of gravity, that's the force that keeps you on the ground. And the electromagnetic force, and that keeps you from falling through the into the ground, into the earth. The weak force, and that keeps you from being bombarded by solar radiation and by cosmic radiation and by meteorites and meteors and asteroids and comets. And the strong force, which keeps you from flying apart. And I'll explain why that is the case later on. And there is associated a particle with each of those forces that is responsible for making the force work, if you like. With the electromagnetic force, it's the photon, which is a particle of light. So when you hold two magnets together, two south poles on two magnets, what's keeping them from touching is light. And for the strong force, there is a particle called the gluon. For the weak force, it's a Z and W boson. They're all called bosons. And did I say for the gravity is a graviton. Now, until recently, they were not able to find the graviton. And there also is another boson that they need to give mass to the other particles called the Higgs. And that was said by Higgs way back midway through the 20th century. And it was only discovered in 2012. Now, to discover all these particular particles, to take it back into the lab, well, the lab in this case is the Large Hadron Collider. It's in CERN, and it's a 27-mile loop of superconductors, all underground, in Switzerland. They take particles and accelerate them near the speed of light in one direction, and then another group of particles the opposite direction, and have them collide and see what they're made out of. Now, at first, there was so many particles, they call it a particle zoo, but then they have narrowed it down to the particle theory of matter, which I've just described. But it wasn't strong enough. There was finally, when they put more, made it stronger, then they were able to find the Higgs boson just in 2012, and that was whenever you have a theory and you have predict something and it happens to be true, it's made the theory more truthful. And the other, they can only, if they tried to go back farther than, say, to find the graviton at 10 to the minus 43, you'd have to have a collider so strong it would have to be bigger than the solar system, sort of thing. So it needed another piece of equipment called the LIGO, where they used interference of waves. And they detected gravitational waves, and therefore there must have been a graviton as well. So there is some collaboration of this particular theory. Now, if I think I said that you're mostly 99.9999999% space. So why don't you fall through the floor then? Well, I guess you're a magician. You can levitate one angstrom unit above the floor, 10 to the minus 10 meters. You don't really touch anything. And why is that? Well, you or your atoms have negatively charged uh, atoms, and the floor has negatively charged atoms as well. And like atoms repel. So that's what's keeping you from falling through the floor. And it's stronger than the gravitational force, and it's called the strong force. So let that force be with you. I have to make a correction. It's not called the strong force, of course. It's called the electromagnetic force. So let that force be with you. Where does the strong force come in then? Well, your atoms are all composed of protons, and they are all positively charged. And positive charges, like negative charges, repel each other, like charges repel. So why aren't your protons, and why aren't you flying apart? Well, there's a force stronger, again, than the electromagnetic force that's keeping all your atoms, all your neutrons and protons at the nucleus of your atoms together. Let that force be with you as well. Now, the weak force is responsible for your radiation. You're a radiant person, but you're not that radiant, actually. It would take millions of years times the age of the universe for you to radiate away through radioactive decay. But it's never less important for you, because without it you'd probably die. It keeps the center of the Earth molten, and the center of the Earth is iron. So it's through radioactive decay keeps the iron molten, and when the Earth circulates, turns, it sets up an electromagnetic field around the Earth, or shield. You have your magnetic North Pole, you have magnetic South Pole, and that shields you from the harmful solar radiation or harmful cosmic radiation coming from space. It also protects the atmosphere from being blown away by the solar radiation, and the atmosphere gives you your oxygen, which you need to breathe, and also deflects or burns up most of the material coming from space, which if it hit you, it would also be a very detrimental. So you get all those forces then in the first second. And in the first second, you have matter and energy being interchanged. And now, before 1905, no one thought you could interchange matter and energy. You have the law of conservation of energy, law of conservation of matter. But Einstein, with his special theory of relativity, said no, they're exactly the same. E equal mc squared. Your energy is equal to your mass, or the amount of matter you have, the amount of material you have, times the speed of light times the speed of light. Now, the speed of light is constant. It's 10 to the 10 centimeters per second. If you measure light coming from a planet and going away from the planet going away from you, it's fine. The light is the same speed. So if you converted all your mass into energy, you'd blow yourself up, everybody else in the room, the building, the city, and some of the surrounding area. So hold on to your mass. Don't explode. But then for every particle that was being created, and that happened about when the strong force separated out, or the weak force separated out, and the electromagnetic force separated out 10 to the minus 12 seconds. So you get particles, and for every particle you get an antiparticle. So for an electron you get a positron, for an up quark you get an anti-up quark, and so on. But at 1/10 of a second you get your protons, and then at 1 second for every billion antiparticles you got 1,000,000,001 particles. And you are made up of particles. If you had any antiparticles, you would explode. Particles and antiparticles come together and annihilate each other and form energy. So you had a chance, 1 in a billion chance of making it through that. Why? Was there the one particle left over? Well, when you go back to the lab and try to change mass into energy, you get the equal number amounts. So science has not been able to know, I can't understand why, at 1 second you got an extra one more particle than any particle. Because without that, nothing would exist. Then we can go on and say, where did you get all your hydrogen from? Because you are made up of mostly hydrogen. Well, for the next 380,000 years, everything was so hot, still hot, and then you had your protons, your electrons, your photons, all swirling around. Couldn't do any combination because it was so hot and so dense. But at that time, then it cooled down enough so the electrons could be captured by the protons. So you get one proton, one electron, and that is hydrogen. So that's where you got all your hydrogen from. 13.8 billion years minus 380,000 years ago. And you thought you were only 100 years old, or less than 100 years old. Now, the other characteristic that you have is your weight. What is your weight? Well, before the 1600s, I don't say nobody knew, they knew. They didn't have a formula, at least. Didn't understand weight that much. But Newton came along and said, no, it's the force of attraction between you and the Earth. And we call it gravity. And the formula that he came up with is proportional, or if you like, equal to the amount of mass you have times the amount of mass that the Earth has, divided by the distance between the center of gravity of you and the center of gravity of the Earth, squared. And what is that called? Well, it's called your weight. Yes. So what you do is you put a mechanical device, we call it a scale, in between you and the Earth, and you can measure what that force is of attraction, attracting you down to the center of the Earth. So, can you lose weight by climbing a mountain? Can you gain weight by going down into a mountain? and down into my mind? Theoretically, yes, but it's so small that you wouldn't notice it because if you compare Earth to, say, a billiard ball, and the surface of the billiard ball then to the surface of the Earth is so negligible that you wouldn't see the difference. Of course, if you went to the moon, then you would. You would weigh much less because of force of attraction, because the mass is so. There's only 1.2% of the mass of the Earth. There, you would only weigh 1/6 as much as you weigh on the Earth. So, if you wanted to, for instance, break some Olympic records like a high jump, you should go to the moon to do it. But not quite what, it's not quite right. There's a more precise definition of weight or gravity. Your weight is basically how much you fall into the warp around a warp of space and time found around the Earth. The mass of the Earth changes the space around it, causes a well or a warp, and you fall into that. And the closer you are to that mass, the harder and faster you fall. This is Einstein's general theory of relativity. Gravity is a warp in space-time. It is not attraction between two objects, as Newton said. Just to get it was a thought experiment, but it was corroborated by an experiment. They took it back into the lab, but they used the solar system as their laboratory. During a solar eclipse, they found that stars beyond the sun were deflected. They appeared in a different place than they normally would. That's because the photons going around the sun traveled through the warp caused by the mass of the sun in space-time and were deflected, so the stars appeared in a different place. And at that time, Einstein became famous because there was some evidence to support his hypothesis. To get maybe another thought experiment to get an idea of what we're talking about here, if you have a rubber sheet representing space-time, and you have two ball bearings, one larger than the other, the larger one representing, say, the Earth, and the smaller one representing the Moon. And then when you roll the smaller one, you place the larger ball bearing on the rubber sheet, or the Earth in the space, and it forms a dent, if you like, or a well around the ball bearing, or a warp around Earth. Then when you roll the smaller ball bearing representing the Moon towards the larger ball bearing representing the Earth, it'll either go, depending on how hard you roll it and how massive the two objects are and how close it comes to the other object, then it'll either go right by or it'll be deflected, like it did with the solar eclipse experiment, and go on, or it'll hit the warp and go around it, like this moon goes around the Earth. So it's not that there's attraction between the moon and the Earth. The mass of the Earth forms a warp in space-time. and the Earth is falling into that. The moon is falling into that. Now, at first, some of the scientists thought warp in space-time. What does that mean? It doesn't make sense. But when they had the experiment, then they had to agree that that is the more definitive way of how the world works. Now, Newton's laws are pretty well used for practical purposes. So it isn't as if Newton's laws are well, they're wrong in one sense, but they're also right. If as long as you have them only apply in areas where they work, then you're fine. And for most everyday experiences, they work fine. Good enough to put men on the moon and to send satellites off into farther than they could go under their own steam by using the force of gravity from other planets to fling them farther into space. But it's not good enough to, for instance, to explain how Mercury goes around the sun, because Mercury's closer to the sun, therefore it's influenced more by the warp caused by the sun's mass. Excuse me. And you need Einstein's laws to explain it more definitively than Newton's. Now also, as I say, time itself changes because of mass, not just space, but the closer you get to a large mass, the slower time goes. Again, we don't really notice the difference because we are pretty well all the same distance from the mass of the Earth. So we occupy the same position in the warp. But if you want to go anyplace and use your GPS, you'd better use Einstein's Einstein's general theory of relativity. Because this time in the satellite, since it's farther away from the mass of the Earth and is farther away from in the warp caused by the Earth, it runs faster than the time on Earth. You need to have a atomic clock to measure it. But if you don't incorporate that in your GPS would be out after 2 hours. So you would not end up where you wanted to if you don't use Einstein's view of how the world works. Now, so if you like, that's a world vision. Einstein has explained how things work. Did he get a Nobel Prize for that? No, he got a Nobel Prize, but for his contribution to an alternative theory that called quantum mechanics or quantum field theory. He explained how the photoelectric effect. So when you're walking through in a elevator and it starts to close and opens again, well, you can thank Einstein for that. Or when you're driving your car through into a garage and the door stops from coming down and hitting your car closely, you can thank Einstein for that too. So he got a Nobel Prize for that. And he didn't like the other view, the quantum view, because quantum mechanics uses uses probabilities. Planck was one of the founders, and he said again that time and space are discontinuous. Whereas in Einstein's view, yes, they were. They're deterministic. And Heisenberg, another founder, said that you can't be certain, really, absolutely certain about one thing if it's related to another. The more you're certain about the first, the less you'll be certain about the second. For instance, if you want to know the speed of a particle, then the more you're certain about what speed is, the less certain you'll know the position, and vice versa. Not because you can't measure the two, it's because that is what happens with reality in the quantum world. And you base all your findings on probabilities. It's only when you, in the macro world, where you combine all the probabilities, do we get something that approaches what we think of being real or reality. He spent the most of his career trying to find the combination or a theory of everything, or quantum gravity. Because in the quantum world, and you don't have to worry that much about gravity, because the masses are so small and the force is so weak that you can pretty well get along without gravity. The only problem is, if you have something small and massive, then you have a problem. So anyhow, I have to stop now because I'm getting allergic to something. You have two world theories, both which have all the evidence supporting them, no evidence to contradict, and yet they're totally incompatible. So science does not know how the world works. Absolutely. It does not have the theory of everything. Or I think God, or as I think Einstein said it as well, once you have can combine the two, maybe then you will be closer to know the mind of God. I'm going to leave it at this and come back to it. Bye.